Welcome, everyone, to our Sarl Vishlation, our simplified analysis of power electronics switching. It's wild when you think about how our entire world basically runs on power conversion. But man, the sheer number of topologies and components out there, it can definitely feel completely overwhelming. So today, we're going to strip all that noise away. We're looking straight at the absolute structural DNA of power electronic switches. We'll figure out what they actually are structurally and how their four specific operating modes totally dictate every aspect of circuit design. Let's dive right in.
Actually, I want to kick things off with a direct quote from our sources today, because it totally hits the nail on the head. Welcome to power electronics. Let's make it simple. यहाँ सब कुछ simplified है, तो चलिए शुरू करते हैं. I absolutely love that tone, and it's exactly what we're going for in this explainer. We're taking some pretty heavy engineering concepts and mapping them out so clearly that you'll literally see the matrix behind how components are selected.
Okay, so here's our roadmap for today. We're going to cover 5 main things. First, the 4 fundamental states. Second, switch physics and structures. Third, matching converters to those switches. Fourth, the topology switching matrix. And finally, the essential component selection rules. Section 1, the 4 fundamental states. So let's look at this Cartesian plane mapping current on the y-axis against voltage on the x-axis. This reveals the 4 fundamental states that literally any power switch has to deal with. First up, we've got forward conduction, or FC, where your switch actively lets forward current flow. Right opposite to that is reverse conduction, or RC, allowing reverse current. Then we get into our blocking states. There's forward blocking, FB, where the switch holds back a positive voltage without actually conducting, basically acting like an open circuit. And finally, reverse blocking, or RB, holding a negative voltage without conducting. Basically, every single power switch out there is defined by exactly which of these 4 states it natively supports.
And what's really cool is how these 4 states map perfectly onto the real-world quadrants of power switching. Say you're driving a motor forward. That operates right there in quadrant 1, which demands forward conduction with positive voltage and positive current. But what if you need to slam the brakes on that motor? Suddenly, you're pushing into quadrant 4, reverse braking, which means you have to maintain a negative voltage but a positive current. So figuring out which quadrants your specific load requires tells you exactly which of those 4 operating states your switch absolutely has to have.
Moving on to Section 2, switch physics and structures. Let's look inside the switch. Now, if you've ever wondered what structurally separates a true power electronic switch from your standard everyday microelectronic switch, this is it. The drift layer. It's a lightly doped N- structural layer, and its entire job in life is to scale in thickness so it can provide high voltage blocking capabilities. Seriously, without this drift layer, a switch would just instantly break down under the intense electrical stress we see in power applications.
But check out this inescapable engineering trade-off here. If you look at the structure, sandwiched right between the anode and cathode of a standard power diode, you'll see that thick N- drift layer. Now, while that structural layer is exactly what gives the diode its superpower to block massive reverse voltages, it also adds a whole lot of electrical resistance. Adding this layer directly results in a practical on-state voltage drop of anywhere from 1.5 to 3.3 volts during forward conduction. So it's essentially a literal toll you have to pay in efficiency just to get that high voltage survivability.
Which brings us to Section 3, matching converters to switches. Let's talk state requirements.
Okay, let's start with the absolute simplest state profile, high-frequency DC-DC chopping. If you just want to step down or step up a DC voltage, your switch structurally only needs to handle forward blocking and forward conduction. That's it. But while the state requirement is super minimal, the performance demand is extreme. This topology demands exceptionally high-frequency switching to regulate power properly and keep your magnetic components from getting massive. And because of those crazy high-frequency demands, transistors absolutely dominate this specific space. We're talking components like BJTs, MOSFETs, and IGBTs. Their highly responsive gate structures make them the perfect power electronic switches here. Even though a thyristor, like an SCR, technically has the forward states you need, its bulkier internal structure just cannot turn on and off fast enough to keep up with a demanding high-frequency chopping profile. No way.
On the flip side, let's look at AC-DC conversion, or rectification. Here, the whole goal is taking an alternating current and forcing it to flow in just one direction to spit out DC. So this topology needs forward blocking, forward conduction, and, crucially, reverse blocking. But here's the kicker. The reverse conduction mode has to be entirely absent. Because of that very specific state profile, the silicon-controlled rectifier, the SCR, with its complex multi-layer structure, becomes the undisputed standard ideal component. It natively supports FB, FC, and RB, making it absolutely perfect for controlled AC to DC conversion. So the really crucial takeaway here is how changing your source fundamentally alters the states your switch has to handle. Let's compare DC to AC inverters. If you're building a voltage source inverter, or VSI, your switches must support forward blocking, forward conduction, and reverse conduction to manage reactive loads. But the second you swap to a current source inverter, a CSI, you don't need reverse conduction anymore. Instead, your switches absolutely must have native reverse blocking capabilities. When you visually map out this divergence in state requirements, you see exactly why component choices shift so drastically. For a voltage source inverter, we need that reverse conduction, right? So engineers often use a reverse conducting thyristor, or RCT. It essentially has a diode built right into its physical structure to handle that reverse flow. But on the flip side, for the current source inverter, because we absolutely demand reverse blocking, the SCR is the go-to. It relies on its native structural ability to block reverse voltage. It's the exact same goal, making AC from DC, but totally different switch selections just based on those foundational states. Finally, we have AC-AC converters. Think heavy industrial motor speed controllers or high-power dimmers. This topology demands perfect symmetry. Since you are directly controlling an AC sine wave, your switch has to support the full spectrum: forward blocking, forward conduction, reverse blocking, and reverse conduction. Because it needs to control both the positive and negative cycles completely symmetrically, the triac is uniquely suited for the job. Structurally, it's essentially a bidirectional switch perfectly built for full four-quadrant operation. Section 4. The Topology Switching Matrix. Let's bring this all together. Now, this master framework brilliantly illustrates the entire landscape of power electronic switching in one single view. Just scan across the matrix. AC-AC needs all four states, so we use a triac. AC-DC drops reverse conduction, so we shift over to an SCR. And as you move down the table toward DC-DC conversion, you strip away the need for reverse states entirely, so we only need forward blocking and forward conduction. The visual takeaway is stunningly clear, honestly. Stripping away required switching states simplifies your topology, and it directly shifts your ideal component choice away from those heavy thyristors straight toward high-speed transistors like MOSFETs and IGBTs. And finally, Section 5, Component Selection Rules. Let's look at some practical heuristics. If you map switching frequency on the y-axis against power rating on the x-axis, you instantly see the grand engineering trade-off in power electronics. Transistors, your BJTs, MOSFETs, and IGBTs, strictly dominate that top left quadrant. They're your go-to for high-frequency regulation, mostly in DC-DC environments where the stay requirements are minimal, but switching speed is absolutely everything. In contrast, thyristors like SCRs and GTOs sit way down in the bottom right. They scale up incredibly efficiently for immense grid-level power ratings, totally dominating heavy AC/DC and CSI applications where those native blocking states are structurally required. To wrap up this explainer today, I want to leave you with a fundamental design rule highlighted right in our sources. When you're controlling an AC output, to eliminate any unwanted DC bias, engineers have to ensure that the integral area of the positive and negative cycles are perfectly equal. So as you stare down your next schematic, armed with this new structural DNA knowledge about drift layers, switching quadrants, and component matrices, ask yourself, how will you perfectly balance those cycles? Which power electronics switch has the exact structural DNA to make your specific design a reality? Thank you so much for joining this serial visualization. Keep questioning, keep designing, and we'll see you in the next explainer.